Hey class, I sent you section 12.4 curve sketching techniques, and so that's what I'm going to go over today. I'm going to go ahead and jump into the lesson, and we're just analyzing f of x equals x over e to the negative x, which has a lot of ideas with intercepts domain, taking the first derivative, the analysis in the previous sections for the first derivative, and then the second derivative, and then finding minimum and maximum points, also with points of concavity and points of inflection. But with that said, and we're going to go ahead and jump into what we have to do here. So first is the domain, and on the domain, we just look at the function. Is there any values that x cannot take on, is usually what I ask. In the bottom, the only issue would occur is if the denominator is 0. This cannot be 0 because it's an exponential function. So you can plug any number in there, including 0, because e to the 0 would be 1. So the domain of this function is negative infinity to infinity. Following up, it asks for the intercepts. So we'll do the easier one, the y-intercept. The y-intercept, you just plug in f of 0 into the function. So it's basically 0 over e to the 0, which is 1. So there's my y-intercept. My x-intercept, I'd have to solve, we'd have to set the equation f of x equal to 0 and solve this. Well, the only way this is going to be 0 is if the top is 0. So my solution there is my x-intercept is x equals 0. So, and then I'm going to go ahead and write the points that we found. We found 0, 1 as the y-intercept. And then here we found 0, 0 as the x-intercept. Because we're going to come back and plot those points. From there, find any asymptotes. Asymptotes are found by setting the denominator equal to 0. But again, just like in the domain, there's no way that the denominator could be 0, so there's no asymptotes. So I'll just put none. Okay, so that's the step 1 part. And step 2, you would want to find the first derivative, okay? So I'm going to rewrite my x over e to the negative x. And the first derivative is going to be found using the quotient rule, okay? So if you remember that little saying I told you, the derivative of the first, which is the top, so the derivative of the top is 1, times the second unchanged, e to the negative x. Here, you know what? Let me change colors on step 2 so that we can differentiate a little bit. Okay, so here we go. The derivative of the first is 1 times the second unchanged, so e to the negative x, minus the derivative of the second, so minus negative e to the negative x, times the first unchanged, over the second squared, e to the negative x squared. From here, I can kind of simplify this a little bit because I can factor out an e to the negative x on top. And remember, that's going to turn to plus. So if I do this, I'll end up with f prime of x equals e to the negative x. This leaves me with 1 right here. Remember, this is going to be a plus. If I factor out e to the negative x, I'm left with x over e to the negative x squared. So you'll see that one of these will factor, okay, and then that's going to leave us with our, and I know it's going to be kind of squeeze it in here because we're going to need the space. Well, I'll just write it up here. So these will cancel. One of these. So you still have 1 e to the negative x in the bottom, actually. So I'm going to be left with 1 plus x over e to the negative x. So that's my f prime. goes 1 plus x over e to the negative x. Okay. Okay, so then the following thing, you want to set, if you want to find your partition values or critical values, you're going to set the derivative equal to 0. So set it equal to 0, I get 1 plus x over e to the negative x. Solve this, well really, the only thing that matters is 1 plus x on the top, which tells me that if I subtract 1, I have my partition value. So we use this on our first derivative test from previous lessons that we talked about. We make the interval, right, and then the two intervals would be negative infinity to negative 1, negative infinity to negative 1, and then the other interval would be negative 1 to infinity. We're going to test values in there, so a value would be negative 2 in here, and then 0. I always try to use the easy one, so y'all know that. F of x, I'm going to plug in f of negative 2, figure out what that is. We're going to plug in f of 0, figure out what that is. F of negative 2 would just be negative 1 over e to the negative 2, negative 2, so e to the 2, which really the bottom doesn't matter. I just know this is going to be negative, so that's all I'm worried about. 1 plus 0, 1, and then e to the 0 is 1, so it's 1 over 1, which is 1. So again, all I care about is that that's positive. So this one's negative. So the result would be on the first derivative. That's going to tell you if if it has a positive or negative slope. Okay. So in this case, that's negative, so it'll have a negative slope. That's positive, so it's going to have a positive slope in that interval. Okay. So I kind of have an idea of how this is going to pan out for the first derivative. We're going to do the same thing, but we're going to do the second derivative now. So the second derivative, I'm going to take the derivative of this. So second derivative of x, the derivative of the first, the derivative of 1 plus x, that's just 1, times the second unchanged, e to the negative x. Okay? It's quotient rule again. Minus the derivative of the second is going to be negative e to the negative x times the first unchanged, so times 1 plus x, all over the second squared. Okay? And so a similar thing will happen like in the last one. You'll be able to factor out the e to the negative x. So we'll end up with e to the negative x on the outside. That's going to be left with 1. That turns to plus. This time if I factor e to the negative x out of here, I'm left with actually 1 plus x. Okay, so I'm left with that over e to the negative x squared. Okay, and then from here I can kind of simplify this, and one of these x's goes away, right? And this is going to be 2 plus x over e to the negative x. So that's my second derivative. So again, you're going to set the second derivative equal to 0. So 0 equals 2 plus x over e to the negative x. Solve that. Again, the only thing that matters is the top to solve this, so I got to set the top. Because if the numerator is 0, then the whole thing's 0. Subtract 2, you get negative 2 equals x. So I'm going to use this for my intervals, right? So I'm going to kind of do a similar thing that I did here in like half the space here. So I know it kind of gets hard to see on this side. So let me see if I can scoot this over a little bit. So we're going to do our interval, which is going to be negative infinity to negative 2, and then negative 2 to infinity. and we're going to test the value. In this interval, I'll test -3, and in this interval, I'll test, 0. Okay, and here we're going to plug those numbers in, f of -3 and f of 0. And I take that back. I know we said we want to plug it into our derivative. Did we do that here? Yes, yeah. But I just want to make sure, because I don't think I put the notation here. Yeah, make sure you put this notation back on this part, because we actually plugged it into, we did do it correctly, we just didn't write the proper notation, because we plugged it into here, which is the derivative, not f. F is the original function, okay? So this one we're plugging into the second derivative, because it's called second derivative test. So from here, I'll just plug in -3. So I'll end up with -1 over e to the -3, which is +3. But again, this is going to be negative, so that's all I care about. F of 0, 2 plus 0 is 2, e to the 0 is 1, so it's 2 over 1, which is 2. So that's f of 0. So what's your result? It's either going to be concave up or down. In this case, it's going to be negative, so it's concave what? Down. And then this one's going to be concave up. Okay, so hopefully you can see that. I know it's kind of small, but so this is the analysis. Okay, in what do they call it? 5 simple steps or 4 simple steps. Except we're on step 4. And then actually one more thing. If you have something, let's look at this. So if you have something that it's decreasing, go ahead, and that was the other thing we put. We called this decreasing too. So that's decreasing, decreasing, increasing. So if you have decreasing, increasing, what is this? Is this a max or a min? Well, if you're going down and then up, well, guess what? That's a min. So I have a minimum according to this analysis, and I'll kind of just squeeze it in here. Min at x equals -1. Why? Because of this, decreasing and increasing. So that's definitely not a max. Here we have concave down, right? Concave down, which actually should be this way, if I draw it correctly. Concave down, so that means it kind of cusp downwards, and then it goes back to cusping upwards. So concave down to concave up, this is called a point of inflection. So when it changes concavity, that's a point of inflection, but where is it at? It's at -2. So point of concavity at x equals -2. Okay, so now normally I'd like to leave all this stuff up here, but I think I'm going to have to erase it if I'm going to draw it. So from what I'll get here is I do need my y-intercept. I know there's a point at 0, 0. I also know there's a couple of other points, but we'll kind of deal with that in a second. So let's sketch a picture of this, see what it looks like, and we'll go from there. Okay, so we're just going to put the main points of interest, which the main points of interest is going to be the point of concavity, which there's the point of the minimum, the critical point. So I'm going to plug in -1 into the original function f of x. So f of x, again, I should have left that part on there. X over e to the -x be f of 1, be 1 over e to the -1, which we can do a calculation, and let me do that real quick. So 1, remember the e button is on second division, okay, so 1 divided by e to the -1 power. I get 2.718, right, which makes sense actually, because it'd actually just be e to the first, which is 2.71. Okay, so f of 1 is 2.71. So I can do 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so I'm just going to put a few points. But f of 1 is 2.71, which is about right here. And we're claiming that's our, it's decreasing to increasing at that point. So that's our minimum. Okay, so that'll be our minimum. Okay, I had to pause it real quick because I knew something was going up here. I shouldn't have plugged in 1, I should have plugged in -1, the critical point. So what that changes is that should be -1, that should be e to the -1, which is 1 over e, which I will have to calculate, which it should be like 1 over 2.71, which is almost a half. Okay, so, but you can calculate it, it would give you a decimal less than 1, but if I were to plot this, it's -1 about a half. Well, right there. So that actually turns out to be the minimum. Okay, so this is my, I kind of label as I go, minimum. I know that's there. I know 0, 1, that's the y-intercept. Okay, and I also have something else up here because f of 0, 0. Yeah, I think I'm getting that from this is not accurate. Okay, so 0, 1, that's our y-intercept. And then what else do we need? At x equals -2, there should be a point of concavity, so I'm going to want to plug in f of -2 as well, just to figure out what that point is. And if I do that, I'm going to get -2 over e to the -2, which turns out to be -2 over e squared. That one I will calculate. Let's see what it is real quick. So let's see. I'll do it using the trace feature. 0.27. Okay. So this would be at -2 is 0.27. So it'd be about right here. Okay. And supposedly, according to this is our point of concavity. So we got 3 points. Okay. Okay. Bear with me because I obviously didn't change the top here. I should have plugged in -1 in for x, so that'd make it -1 over e, which would make it down here. And the point exactly would be -0.36, or estimated. So I would actually want that point here would be below the line. Okay, so, and then this obviously as well would be negative. So this is the coordinate -1, -0.36, and then this would be the coordinate -2, -0.27. So about closer and closer to that. Okay, so, and then just to kind of reiterate, this one is supposed to be the minimum, and then this one's supposed to be our point of inflection. Okay, and then from there we got kind of the key points, and I would encourage you to use your y equals feature from here, but this is the analysis. Okay, that's the important part. You have the analysis. I put it excuse me, I put a couple of the key points on here, and what you'll see if you look at the graph on your calculator, and I'll do this in a different color just to kind of emphasize what this will look like. You'll see that on this side it kind of tends towards the x-axis, and then it goes concave down here, but then after it turns concave up. It's very subtle. Okay, concave up, and then it'll start to increase through and look exponential after that. And so that's kind of a rough sketch of what your graph looks like. Now, why not just do that from the beginning? because we're looking for the key points. Okay, and I'm interested in the analysis. Okay, here's the analysis. Can you take the first derivative, take the derivative, set it equal to 0, find critical points, create intervals, test some values, and then see if it's decreasing or increasing or negative or positive, and then determine if it's a max or min. And then can you take the second derivative, set it equal to 0, create intervals out of that, and then test values in those intervals and see if it's concave up or concave down, and find the point of concavity, if any. That's what I'm interested in. Okay, so that's kind of the complete analysis. Again, I encourage you, use the y equals feature on your calculators to kind of help you see if you're on the right track with some of these. Okay, all right, so that's the first one. On the back of that paper, or the second part of that paper, you have another equation. Let me erase this. And that one's about cost. Okay, and hopefully you can see that. I know it's kind of small, but I'm working on getting a bigger board. So the cost is equal to x squared plus 2x plus 2,000. X CD players are produced in one day, and the cost per day is represented by this cost function. And the average cost per unit is the cost divided by the number of units. That makes sense, right? Use the graphing strategy to analyze the average cost function. So first, the average cost function is the cost divided by x. So here it is. That's the average cost function. Second, we want to find the domain of this. Okay, well basically, x cannot be 0, right? So then my domain would be negative infinity to 0, union 0 to infinity. But except, does it make sense for me to produce negative units? So here we talk about reasonable domain. In this problem, doesn't make sense for me to have negative units. Therefore, your domain is only going to be 0 to infinity. So from here, we look at intercepts. Okay, the top is a quadratic equation, and I can kind of tell, but we'll work it out, that well, here, let's start with the easier one, like we did last time. Y-intercept, that's easy. F of 0. So, meaning cost of 0. So 0, 0, 2,000 over 0, and it's actually no. So that means does not exist. There's no y-intercept. Okay, which probably means that there's going to be an asymptote there. So that's what we're going to do coming up. Is there a horizontal asymptote? Well, actually, before that, what about the x-intercepts? Set the equation equal to 0. Solve for 0. The only thing that matters, I told you, is 0 equals x squared plus 2x plus 2,000. Okay, the top, the numerator. If we try to solve this, and I can do it using, I could try using my calculator. You'll see that you'll see on your calculator this graph will not go through x-axis. You might have to change the window up a little bit, but by hand, if you did negative b plus or minus the square root of b squared minus 4ac, because it's a quadratic, I can solve this. But sure, we'll do this real quick. So b is 2, so negative 2 plus or minus the square root of 2 squared minus 4 times a is 1, c is 2,000 over 2 times 1, which here, this is going to be 4 minus 8,000, which is going to be a negative number. Square root of a negative number is imaginary, therefore that right there tells me there's no solutions to this. So therefore, if there's no solutions to this, then there's no intercepts. No x-intercepts. Because that's what we're trying to find in the first place. Okay, so no x-intercepts, horizontal asymptote. Okay, let me just kind of remind you some things. So if you have a polynomial function, or even better, if you have a rational function, and then on top you have an x to the n plus an minus 1 times x to the n minus 1 plus dot 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 a1x plus a naught over another polynomial bm x to the m plus am x to the m minus 1 plus dot 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 a1, or I'm changing this up, b, there should be b's in the bottom, b1x plus b naught. Then you have a couple of possibilities. Okay, one, if the power on the top matches the power on the bottom, or here we'll start with if n is less than m, horizontal asymptote is y equals 0. So that's nice and easy. If n equals m, if the power on the top matches the highest power on the bottom, the highest power on the top matches the highest power on the bottom, then your horizontal asymptote is y equals the coefficient of the top, degree, divided by the coefficient of the bottom, which, whatever the lead terms are, the terms with the highest powers. So that's that. And then if it's if n is greater than, if n equals the bottom plus 1, in other words, if the top is 5 and the bottom's 4, then you don't have a horizontal asymptote. Use long, I think that's what we're going to have to do here, use long division, polynomial long division, to find slant asymptote. Okay, so which is what we're going to have to do, or also known as oblique, which is, that's what it says on your paper. Oblique asymptote. Okay, so this case, the power on top is 2, the power on the bottom is 1, so I'm going to have to do just that. So I'm going to have to do x squared plus, here, let's do it in this little, I already know space is going to be a premium here, so I'm going to do this right here. X squared plus 2x plus 2000 divided by x. Okay, so how do I do this? I just look at the lead term here, and the lead term here I'm going to divide. X squared divided by x is x. Multiply that, x times x, x squared. Subtract it. I'm going to get, that cancels out, bring down the 2x. 2x divided by x is 2. 2 times x is 2x. Subtract that, bring down the 2000. The 2000 has no x term, so actually that turns out to be the remainder, but that doesn't matter because this is the only thing that matters. That is the oblique or the slant asymptote. Okay, so we'll kind of deal with that in a little bit. So that's the slant or oblique asymptote. Okay, so we have all that. That's that was step 1. Step 2 is analyze the derivative. Okay, so we'll go for that. So the derivative of the cost function, or the average cost function, is going to be x squared over x. X squared. So it's another quotient rule. It's going to be 2x plus 2, the derivative of the first, times the second unchanged, minus the derivative of the second, which is x, which is 1, times the first unchanged, x squared plus 2x plus 2000. All over the second squared, all over x squared. So we're going to simplify this, see if some of the top cancels out. here I'm going to get 2x squared plus 2x if I distribute that x. And then here I distribute the negative, so it's negative x squared minus 2x minus 2000. I don't need that parentheses. Okay, over x squared. Well, here's the good thing. The 2x cancels out with the 2x. 2x squared minus x squared, that's x squared. And then minus 2000 over x squared. So we found the first derivative. Okay, so now we have to analyze this. We set it equal to 0, just like before. Okay. So x squared minus 2000 over x squared. But again, only the top matters. Okay, only the top matters. So we're going to solve this for the top. X squared minus 2000, which if I add 2000 to both sides, I get 2000 equals x squared. Take the square root of that. I'm going to get x equals plus or minus the square root of a 2000. Okay, so this is actually my, those are my critical points. Okay, those are my critical points. Okay. Okay, so then we're going to continue, and I went ahead and calculated the square root of 2000 is 44.721. So it's positive or negative 44.721. Okay, so what's next is we got to do the intervals. Okay, so the intervals, this time since I found two critical points, two partition points, you have to do 3 intervals. Negative infinity. I might give myself more space because I'm gonna need it there. Okay, so interval would be negative infinity to negative 44.721 to and then the negative 44.7. Yeah, 44.7 is fine because we don't need all that decimals. Okay, to negative 44.7 to positive 44.7, that interval between the two solutions, and then the interval after 44.7. Okay, so this is our test value. I'm going to just pick a number in here, so maybe like negative 50 comes to mind. Also over here, I could pick 0, although 0 is not in the domain, so that's not a good idea. So probably 1. And then 44.7, I could probably pick positive 50 is, yeah, what we can do here. Okay, so in this case, what we could also realize too, okay, and this is something I didn't think about till now, but x is what? X is number of units produced, so actually this is irrelevant. I mean, we could do the test anyways, but we could do a little bit less on that. So here, f of negative 50. So we're going to do our, we're going to substitute our values. So f of negative 50. And I'm using the table feature. If you go to second window, which is table set, put it to ask, and then go to second graph. This is after you put your equation into this equation into y1, and then go to second graph after you do the change it to table set to ask, and then you just type in negative 50. It'll give it to you. That's negative 88. Type in 1, it'll give you that's 2003, and type in 50, that'll give you it's 92. So that's a pretty efficient way of doing that. So here on this interval, because we're talking about the first derivative, oh, you know what? I messed it up there. I want to plug it into the first derivative, so I need to put it. Okay, so I erased what I had here. again, we want to plug it into the first derivative, so you should type in the first derivative into y1 or y2, x squared minus 2000 over x squared. So after doing that, going to second table set, changing it to ask, and then go to second graph, type in negative 50, and it'll tell you that f of negative 50 is 1/5, f prime of 1 is negative 199, and f prime of 50 is equal to 1/5. So again, all I care about is it increasing, decreasing, okay, or positive, negative. So this is positive, so it's increasing. That's negative, so it's decreasing here. And that's positive, so it's increasing. Now, one thing we didn't say here was that there's a vertical asymptote at x equals 0 because the denominator equals 0. So, which is going to tie into this, I think, a little bit. Here you have decreasing, increasing. What does that indicate? That would be a minimum. And then here you have increasing, decreasing. What does that indicate here? That would be a maximum. But again, that's negative x's. In this situation, x represents the number of CD players, right? So it won't really matter for this interval necessarily. So we're kind of more focused on that interval. But what does this tell us? That this is going to be a minimum at 44.7. Okay, minimum at 44.7. So from there, I'm going to erase some of this stuff. We're going to get our second derivative. Okay, so our second derivative, we'll just start from here. Derivative of the first times the second unchanged. So derivative of x squared, which is 2x, times the second unchanged, which is x squared, minus the derivative of the second, which is x squared. The derivative of x squared is 2x, times the first unchanged, which is x squared minus 2000, over the second squared. So from here, what I can do is simplify the top, which that's 2x to the third, minus 2x cubed, minus plus, because negative 2x times negative 2000 is positive 4000x over x to the fourth. Then I see I can factor out 1x at least, and here's a shortcut. You can factor it out. Well, okay, I'm going to do the steps because I know that's what y'all want me to do. 2x squared minus 2x. Well, okay, I should have seen this from the start. That's nice, right? 2x minus 2x, that's gone, so it's just 4000 over x. That's even easier. 4000x over x to the fourth. Which one of these will cancel? So, which that'll equal 4000 over x to the third. Set that equal to 0, we will find there are no solutions to this. So there's no points of concavity. No solutions. So in other words, I don't have to do my, there's no second derivative. Well, there is a second derivative test. It'll just be one interval, negative infinity to infinity. Okay, whatever it is, it's just going to be one concavity in that interval. Okay. Now there are no solutions for this, but there is a vertical asymptote, which would be considered partition points. So at x equals 0, because if you put 0 in the denominator, that's going to be 0. So that changes this up a little bit, because if I want an interval, you got to use also the partition points anywhere that's applicable. So in this case, here we would want to do from negative infinity to 0, and then 0 to infinity. And I'm going to test that interval and I would end up getting, I could plug in -1, and I can plug in 1 here. And then if I do that, I'm going to do f of x equals to f of -1. And I'm going to put f of 1 here. Okay, so we'll plug those in. We'll put it in our y equals maybe y3. I'm gonna put the second derivative in there. No. Okay, so doing the trick, you put this into y3. You can turn the other ones off and go to the table. Input -1, input 1. You get -4,000, +4,000. The only thing that matters is that that's concave up or down. And in this case here, we have that it's negative, so it's concave down. And here it's concave up. It's positive. So you might want to say that's a point of inflection, but you got to remember that we had that vertical asymptote. That eraser here was at x equals 0. So a point of inflection has to be kind of like this continuous point where it's going concave down, and then it shifts to concave up. See, it's concave out and up to here, and then up after that. So in this case, it's not like that. It's going to be some kind of asymptote, but we'll see it in the picture when we graph it all. And then on that note, I did kind of miss one interval here, but it actually doesn't matter too much so, but I think it's important to talk about. Kind of like what I said here, not only are you solving for the top, you're also solving for anything that makes the denominator equal 0. So this would change, I would have to change this interval to 0 because this has a point at 0. But like I said, that doesn't change too much because I already tested a point in there. And then I'd actually have to change this from -44.7 to 0. If I wanted the full analysis of the full graph, and then -infinity to -44.7. Okay, at this point I don't think I'm going to go back and do that, but it still works out because most the numbers we used are in these intervals. We didn't test this one, but again, that's not going to matter too much because you can't produce negative CD players, which you probably already forgot about that. That's what we were talking about in the first place, right? So now I have my analysis. Now I need to graph this. So I'm going to do it in this little space here because there's just not much else. So on the graph, I'm going to kind of summarize some of the things. I wrote in here the derivative. So I have the original cost, average cost function, derivative, and second derivative. I'm putting all this here before I graph it, and I'm going to give myself some more space to graph it. I'm also going to need that the vertical asymptote is x equals 0. Okay, if you remember, we didn't have a x-intercept or a y-intercept. So I'm going to look at some of my other stuff. I have a minimum at 44.7 and a max also because it's this is decreasing, so that's a max at -44.7. So max at x equals -44.7, min at 44.7. And then what else is important? We have we already talked about this, the 0. Okay, so which is all we need here. Oh, and our oblique asymptote. Okay, so I'm just kind of summarizing everything we found, which is a lot, right? But we're going to do that. Okay, so now for the graph. Again, use the guidance of your calculator. Go to y equals, and I would go to y. In fact, I would have all three of these here. Go y1, y2, y3, but this time we're only worried about y3. There's a little button on the, or there's a little, if your equal sign is bolded, that means it's activated. So to unbold it, you click on it and you push enter, and then that'll unbold it. So the only one you want bolded is your y3, which should be the second derivative. And I think I had an easier form of the second derivative. Let me get that, which was it should be, so that's x to the fourth plus 4,000x. So it's 4,000 over x to the third. Yeah, you have it there, 4,000 over x cubed. Okay, 4,000 over x cubed. So that was the easier form of that. Okay, which that's what I'm gonna want. So bold the second derivative, and we're gonna graph it. No, not the second. Bold the first derivative. I mean the original function. The original function. So I'm gonna, because that's what we're trying to graph in the first place. Now, on your window, I would suggest if you go to window, go to negative 100. Okay. And then positive 100. Okay, and then yeah, just we'll graph from there. But 1, 2, 3, 4, 1, 2, 3, 4. So that's negative 50. 1, 2, 3, 4. 1, 2, 3, 4. It's positive 50. And then on your y min, I would do negative 200, and then positive 200. We don't have to do too much. Maybe by 50 is there. But you can also do this, the x scale 10, and then the y scale you can do 10 as well. But maybe for paper purposes or graphing on here, I'll go by 50s. Negative 100 actually. It's negative 50 and then negative 150. So from there I graphed what I have. Right, I know the vertical asymptote is at x equals 0. I'm going to put that in there. So there should be a vertical asymptote here. I also know that we have a max at 44.7, or min at 44.7. So if I plug that in, I'm going to plug in both of them. So I'm going to plug this one and f of 44.7 for my minimum. So into the original equation, we will get negative 44.7 is negative 87.44. Okay, and then positive 44.7 is positive 91.443, which you can confirm that if you trace your graph at those points. Negative 44.7, you get about that, and then positive 44.7. Okay, you get 91. So I can graph those points. So negative 44.7 would be about right here, and down to negative 87.44 would be about right here. So I'm going to see a max around there, and then I'm going to see a min around here at 44.7, which is about this, up to 90, which is about here. And you'll just kind of see, I can trace some more points. Like I can just get like the number 1. I'll see it's 2003, so that's kind of high. I don't want to graph that one. Maybe the number 10 is 212. So 10 would be 212, which I would estimate about right here. So maybe we can get negative 10. It's negative 208, so negative 10, about negative 208, about right here. And you'll kind of see maybe like negative 70. Just do the trace feature. You get about negative 100 or negative, yeah, about close to negative 100. So negative 70 be close to negative 100. And so you can kind of see how this graph is oriented. So be guided by that. But you know what, before I even do the other one, graph on your calculator, go to y equals, and I want you to graph the oblique asymptote, and I want you to see that x plus 2. What you should notice is that this graph, the oblique asymptote, if you think about x plus 2, starts at 2, right? Plug in 50 into that, you'll get about 52, which is about right here. Then plug in negative 50 plus 2 is negative 48, so it's about right here. So if I kind of go with the graph that I have, you'll notice that this is the oblique asymptote, and usually you put a dashed line. But more importantly, this line guides the graph. So it's going to guide this direction here, and it's going to guide on this side too. Okay, so that's pretty much the function that you would use there. But okay, just to reiterate, they're kind of the same process. You will have to use a lot of the skills that we used in the prior sections, okay? I don't know if I have time to cover all that, but I did cover a good chunk of it with two pretty tough problems. But the ideas are there. You'll have to take you'll need to analyze the original function, then you'll need to analyze the first derivative, set it equal to 0, find your critical points / partition points, set up intervals, test those intervals, plug in points, see whether it's positive or negative, and then determine whether it's going to be increasing, decreasing. Find your second derivative, set that equal to 0, create intervals out of your critical points / partition points, test values in those intervals, see whether positive or negative, and then you determine whether it's concave up or concave down, which everything should match up with what we had on our analysis, right? So our max is here, our min is here, right? And then from there, we have our asymptote is there, and what else? We had that it was decreasing until here, increasing here, decreasing, well, I don't know if we analyze this part, but decreasing here after that. So everything should match up with our table perfectly, okay? And we also had that after 0 it was concave up, and before 0 it was concave down. And then because of this asymptote, that wasn't the point of inflection. But okay, so that's it for this video. I'll see you guys in class next Tuesday. Your homework is posted. All right, good luck.